Good afternoon, everybody. The idea for today is to talk about one of those topics that seem to be completely aside from the main course of the content of the course. But on the other hand, is actually quite central in many ways. When we talk about perception in audio, when we talk about how we hear things and how we perceive the things that we hear, we actually are laying down the ground to understand how to design a system after these constraints that are part of our perception and our understanding of the things that we listen to. There are quite a few things that are important to understand about the hearing system, and to be honest, to talk about this topic with a certain degree of completeness, it would take us probably an entire course, and we are just trying to do so in a couple of hours. So this is going to be a very compressed crash course for all of you. We will have chances to discuss some of the topics that I'm going to cover with a little more in-depth analysis of some of the topics later on, and especially when we come to the point in which we need to understand more about it because we are designing a system. On the other hand, before then, I really would like you to understand how our hearing system works and how we go about interpreting the things that we hear based on our understanding of the physiology of the hearing system. So, elements of psychoacoustics, kind of a reduced title for a topic that should be much wider. But we will begin with something that is not very psychoacoustic, but is really more physical. I'll give you a very cursory explanation of how the human ear works during acoustic perception. So here's what it looks like. The ear is divided into three parts. Let's say we have an acoustic part, merely acoustic part, the outside of the ear, which includes the pinna, includes the ear canal, and then we go into the mechanical part of the system, which is made of a bunch of little bones, and I'll tell you how they work together. And finally, we'll go into the more electrical part of the system. We go from acoustic to mechanical to electrical design of our hearing system. The reason why I want to go in depth that much is because the critical part of our discussion is really inside the inner ear. So the outer ear is made of the earlobe. Well, earlobe is kind of reductive because the earlobe in English would be just the bottom part of your pinna. So let's say the entire pinna, okay, the padiglione auricolare in Italian, and the hearing duct, which is the ear canal, the hole that goes all the way to the eardrum at the very end. So this is a part that has a very acoustic role. So basically, it has two functions, and well, quite a few more than two, to be honest. But in practice, what it does is to perform some filtering of the let's say, of the sound that he perceives. And at the same time, it performs also a little bit of focusing. So because of the shape of our pinna, we are able to focus our attention more in the forward direction. But that's not the only thing. There is a lot more about it. And in fact, there is a lot of frenzy about how we actually perceive 3D audio just with two signals. Have you ever wondered about it? How can you localize sources around you, despite the fact that you only have two signals that you're analyzing? Well, it's really related to the acoustic response of your body. Your body has an acoustic response. It reacts to the acoustic sound field that it is immersed into, and which means that if we have a source in a certain direction, it will be filtered in a certain way. But if the same source is moved into a different location, it will be filtered in a different fashion. So the variation of the filtering properties that arises from the interaction between our body and the acoustic sound field causes different colors in the sound, which allow us to localize sources in space. To be honest, it's not the only perceptual cue that we exploit in order to localize sources around us. There is also the so-called ILD and ITD, the intralateral time delay of arrival of the acoustic fronts. So if something is on the right, it first reaches the right ear and then the left ear, and vice versa. And also the intralateral level difference, so ILD, intralateral level difference, which means that if something is on this side, because of the shadowing performed by our own head, it will be louder on this side than it is on the left-hand side. So all these cues put together, including also motion cues, the fact that we move around the object, that we do a little bit of interaction, give us an idea of what the acoustic scene is like, what shape it has, and where objects are. So all these things will become particularly important in the second part of the course. For the moment, I just want to focus on the structure of our hearing system. So let's focus on that, and just be content with the notion that your the outer ear, so the pinnas and the ear canals, will help you focus and will help you filter things out. Now, there is one fact that you need to know. We are animals. We are animals, and we have evolved as animals in order to, specialize ourselves into the perception of specific targets. Animals, especially predators, learn how to become very sensitive to their prey, and so they learn how to catch them, basically. If you think about the bats, they developed mechanisms that are based on the emission of ultrasound and the analysis of the returned, the bounced off acoustic field that comes back from the target. Ultrasounds don't propagate that far, so it's going to happen only in the near field, just to be honest, but they will be able to catch a fly with that kind of frequency. Well, we didn't evolve with the specific purpose of catching flies, though it's a very funny thing to do when you're at home. Just try. You'll see that you will have a hard time doing that. There are reasons also for that, perceptual reasons for that. We'll talk about that another time. However, our perception has evolved in the past few thousand years, well, a little more than a few thousand years, in order to maximize the throughput in interpersonal communication, meaning understand each other's speech, being able to have a conversation in a crowded room, like in this case, being able to discern what a person is saying despite the noises around, despite the reverberation. In order to do this, there are quite a few mechanisms that we employ, and we'll discuss them all as we go along with the course. But the minimum thing that we can do is to try to make sure that our hearing system is maximally sensitive to the frequencies that are produced by our speech. And if you think about the distance between our ears, think about the size of our lobes, of our pinnas, you will immediately recognize that the frequencies that are comparable to these dimensions are actually the vocal frequencies. So when it comes to detecting a speaker and getting the most out of the conversation, you will find that the speech will be, that our hearing system is maximally tuned in order to maximize this throughput in the conversation. There are many other things that happen, but for example, the filtering per se is actually a bandpass filter. So it takes away many of the low frequencies, many of the high frequencies, because most of the information in speech is actually in a range of about 5,000 or 6,000 hertz, starting from about 100 hertz. So you don't need big ears, fortunately, but you just need the size that is adequate for that kind of frequencies. In fact, you will, if you think about, yesterday we talked about wavelengths. The wavelength is important to assess what the size of the hearing system, microphones and so on, is expected to be like. Well, in our case, the lowest, when I speak like this, my voice doesn't go below 100 hertz. A woman will speak about one octave above my frequency. So let's say the women speak with a frequency that starts from 200 hertz up. And so it really changes, but let's say we can be safe with the range that goes from 100 hertz, let's say, to 5,000, 6,000, or 7,000 hertz. When you really, if you're a smoker, you will have higher frequencies, but I assume that none of you is anymore, I'm hoping. So the shape of the pinna serves this particular purpose. getting enough stereo image, so the distance must be adequate for that, having a little bit of focusing, so the shape of the pinnas is meant to help you with that. And then one other important thing, the size of your ear canal is actually very small. It's small enough that, that space basically doesn't matter anymore, because it's always smaller than the wavelength of any frequencies that you might be interested in. This is why I insist on the fact that you actually perceive sources in their location in space, despite the fact that you truly have one-dimensional signals. So you have audio signals. You start with a pair of audio signals, so not space-time signals, not acoustic signals. These are audio signals because the ear canal is too small for space to matter. Is this clear for you? Then eventually we're going to have to go back to discussing the so-called HRTF, the head-related transfer function, and the body-related transfer function, because our own response to acoustic field will be crucial to understanding how we perceive 3D audio and how we can reproduce 3D audio, for example, using headphones. So that is actually all that we can say in this course about the outer hearing system, the outer ear. The middle ear is quite important as well, though we will just fly over it once again. The middle ear is made of an eardrum, so we have a membrane at the end that closes up the ear canal. This membrane transmits the vibration, as you can see from the image up there. Those yellow bones there are actually a mechanical transducer. Are you familiar with the notion of a transformer in electrical systems, right? You know that a transformer is a nearly transparent electrical object that transforms voltages and currents in such a way that their product remains constant, so it will have constant power, so you don't have loss of energy in that operation. But you start, for example, from high voltage and low current, and you go to low voltage and high current, for example, just to give you an idea. So it's a nearly transparent object that does a conversion without being lossy in this operation. Well, that system is a system of levers that is expected to do pretty much the same thing. The reason being the fact that you have a large membrane at the end of the ear canal, the eardrum, and a small membrane corresponding to the other side. You can see there is the so-called, there is the last bone, the yellow one, that attaches to the cochlea, which is a snail-like organ inside your inner ear, which has another little window. It's similar to the idea of the eardrum, but it's called the oval window, which receives the motion on the other side and transfers it into the liquid that is inside the cochlea. So, because you have in-air membrane, which is the eardrum on one side, and you have a smaller window that interfaces with the liquid on the other side, you need to perform some sort of a conversion. So you have to go from low pressure, high surface, so low force on high surface, which means low pressure, to something that requires high pressure on a small surface, right? So the same amount of energy that needs to be distributed over a much smaller surface. So you need basically a transformer. And the levers that are depicted there, the three ear bones, they tend to perform this amplification of the pressure and consequent reduction of the motion in order to pass that energy into the liquid, the perilymph, that is included inside the cochlea. Is this quite clear? Obviously, this operation is not completely lossy. We don't have, ball bearings or anything like that inside. So you have to be content with a certain efficiency of transmission of this energy, and which is usually more than enough to be so sensitive as to, detect rustling leaves at a certain distance, or a pin drop on the table in a different room where you are. So there is quite a certain degree of sensitivity that we can attribute to this system, despite the fact that these are very lossy systems after all. Let me stress this aspect. Ear bones, says here, amplify pressure and reduce motion. Why did I talk about transformers? Because it's the same thing. Pressure corresponds to a voltage, and motion corresponds to a current. Force, velocity have the same roles of voltage and current, respectively. You will see that there is an equivalence between mechanical system, fluid dynamical system, electrical systems, which we'll be stressing a lot in the second part of this course. So we'll come back to this equivalencies because we will be using also equivalent circuits in order to model basically physical systems such as musical instruments or the circuits that you use for making sound effects on your guitar. And we come here to the third part of the hearing system, which is given by the so-called inner ear. The inner ear is basically the cochlea. The cochlea has everything inside. So one of the most incredible transducers that you can find in nature. And it's very interesting because it's basically a cone whose length is about 13 centimeters, so 130 millimeters of length. Imagine taking this cone and start rolling it up. Okay, that's how you build a cochlea. You can do that in your own garage. I'm kidding. So the cochlea is this pipe, which, you know, it's really a conical pipe, which is cut in two inside by a membrane, which is called the basilar membrane. The basilar membrane is there in order to collect the electrical signals. On the other thing that I mentioned before and I'd like to insist on is the fact that the liquid that is inside the cochlea is called perilymph. So the speed of propagation is not the same as in air. In air, you remember in water, the speed of propagation is about 4 times the speed of propagation you have in air, almost 4 times. So this is perilymph, is very similar to water, but it's got other things inside, and we're not talking about that. But speed of propagation is different. You need a certain energy in order to start propagation in there. It kind of dims down more slowly than in air, so the absorption effect is a little more limited. That's kind of cool. Inside the perilymph, therefore, we need to have something that catches these vibrations, these wave pressures. In order to do so, you have basically 30,000 hair cells. They're also called neural receptors. Those 30,000 hair cells actually behave like little filters, actually resonating filters, to be more precise. Imagine each one of those hair cells to be pretty much like a mass, like a little mass with a spring underneath, right? If you build a system like, well, there is also a little bit of a friction. But if you have a system that is built mechanically like a mass and a spring, it behaves like a second-order oscillator. So you give it a little shock, and you will see that it will start oscillating, obviously. In this case, they move this way, okay? So they are fairly rigid, but they tend to vibrate of their own accord. So if there is a stimulus coming like a wavefront that reaches them, or if there is like an acoustic stimulation, they will start oscillating depending on the frequency content of the stimulus. Imagine being in a stationary situation where you have a periodic signal or like a stationary signal that reaches all of these cells, all of these hair cells. Well, depending on which frequencies are present in the stimulus, you will have that only some of these hair cells will start vibrating. Those that are reasonably well tuned with the presence of frequencies in the stimulus itself, correct? So if I have a sinusoidal signal that I'm using in order to excite the vibration of these hair cells, so I'm listening to like a tuning fork, just to give you an idea, only those cells that are at the same frequency, they have their natural oscillation frequency, that are pretty much at the same frequency of oscillation of the tuning fork at 440 hertz, they will start vibrating. Because we're not so infinitely precise in having the frequencies, each one of those cells will actually be sensitive to a number of frequencies around their center of oscillation. So I will have a certain type of cells that vibrate exactly at 440, but others that vibrate a little less, they will be less sensitive to frequencies at 440, which means that you will have sort of a bandwidth of sensitivity for each one of those hair cells. So as we can imagine, we have basically a filter bank. Your receiving system is basically a filter bank made of a bunch, 30,000 to be precise, filters that are tuned around different frequencies. And these different frequencies are regionally distributed over the basilar membrane. Actually, they will have a growing frequency of natural oscillations that will go from the lowest frequency around 20 hertz, let's say, to all the way to 20K, maybe 22, except those at 22 will die very soon. Your frequency sensitivity will, of course, diminish as you grow older to the point in which around 40 or 45 years old you can only perceive around 16 kilohertz and maybe 14 when you're 60, to give you an idea. But still, it's a pretty good range if you think about it. There are quite a few things that we need to say about the frequency distribution over the surface of the basilar membrane. Remember, I said before that you have quite a lot of room for placing 30,000 of these filters. And the room is about 130 millimeters. One thing that you discover right away by simply dissecting one of these, you can do that with any of your friends, is to measure the resonance frequency of them, and you will discover that every 3.5 millimeters, the natural oscillation frequency will double. So it will go, let's say, from 440, if you're catching the middle A of your piano as a fundamental. If you move 3.5 millimeters, 3.5 millimeters, you will get twice the frequency, 830 and 80. You move another 3.5 millimeters, you go at 16, you double again the same frequency. So you go at 1760, okay, and so on. This is kind of interesting if you think about it, because it's telling you that for every fixed interval, I am growing by in sort of an exponential fashion. I have an exponential growth of frequency. And this is why you have the piano organized that way. Think about the keyboard of the piano. It's organized with the same kind of exponential progression. If I move, this is the position for 1 octave. If I move on the keyboard every time of 1 octave, I'm actually moving with the fundamental of regular intervals on the basilar membrane. I'm moving every time 3.5 millimeters, because 1 octave corresponds to doubling of the frequency. So get used to the term octaves, because octaves are very much used in sound processing, and they all come from the fact that we have an exponential, an exponential progression in like a geometric progression in the frequencies by moving every time of the same interval on the basilar membrane. So we have to use octaves. We have to use exponential growth in that case. Is that clear so far? I think I said pretty much the important things about this, but I haven't talked about the consequences yet. The fact that we have a filter bank with heavily overlapped filters is going to bring us to interesting conclusions in our perception. On one hand, we have a sensory system that is imperfect because we don't have highly tuned filters. On the other hand, we have a sensory system that is very robust. So if anything happens to your hearing system, maybe locally in frequencies, there is always a lot of redundancy. So you will still be able to function in society, have a conversation, listen to music, and so on. Now, we can talk about how this is going to happen. This is actually quite important. For example, are you familiar with with the reasons why you might have hearing problems, hearing defects. Well, there are many reasons why you might have problems in hearing. Definitely one of the reasons that should worry you the least is being exposed to blasts, because it doesn't happen that often, first of all, but it's not that the reason why you have damaged hearing system. You might have a damaged hearing system due to viruses, due to illnesses of some sort. That is also not so frequent. The reason that is frequent, the most frequent reason why you might have hearing problems is actually constant exposure to loud signals, not necessarily super loud signals, but loud signals. So in order to understand this mechanism, let me tell you a couple of things. First of all, how, because we haven't talked about it yet, how do you convert mechanical oscillation on each one of those neural receptors that are present on the basilar membrane into electrical impulses? Because that's all the brain is able to read and interpret. The brain needs to receive electrical impulses. Well, it's very simple, to be honest. If you take one of those hair cells, think of it as, like a little rigid bar. Imagine that rigid bar being shaped like a reverse T, to give you an idea. It's not the way it is. They're actually shaped in a slightly different fashion. They're built in a, you don't even recognize it as an oscillator if you look at it. I have a microscopic image, I'll show it to you. But for the moment, just for the sake, for peace of mind, think of those as your rulers, those that you use for draw straight lines. And imagine making it vibrate, okay? And beneath the ruler, one of the ends, there is a T. Okay, now this T does this, as it vibrates this way, it will move this way. Underneath the T, because this is a rigid portion, there are some neuroreceptors, or neuroemitters in this case. The neuroemitters, when they are squished, when you step on them, they will react by basically firing an electrical impulse. As simple as that. So we have a bunch of angry electrical emitters that when something steps on their toes, they start firing their electrical impulses. That's how it works. So if you have a very strong vibration, you will step on their toes quite often, right? And you will step on their toes quite heavily, which means that the density of electrical impulses that are fired by this system will become higher, larger and larger. So you have a high density of electrical impulses. The brain will not count them, but it will look at the density. How many impulses do I receive every time unit? Well, if it's large, that means I have a strong excitation at that frequency. If it's low, I don't have much of a strong excitation. But now, how do you protect yourself from this kind of situation? Well, we do have protections in every other, sensing system. For example, our eyes are equipped with an iris, right? If you think about the amount of light that there is outside of the door, and when you go outside, is orders of magnitude stronger than the light that you have inside. That's the reason why when you walk in front of a window, even with the light on and outside there is sun, it looks black, because there are orders of magnitudes of difference in the intensity of the light from outside to inside. In order to equalize this sensation, there is an iris that closes and opens depending on the stimulation of the light. We have a similar mechanism with our hair cells. The hair cells possess sort of an iris which is based on, it's like a faucet that is based on the blood urination. When the intensity of the firing becomes too much, the brain, in order to reduce the intensity and kind of avoid sensory overload, reduces the blood urination of the basilar membrane, and it goes into zones. So if you reduce the blood urination, basically you render your neural emitters a little more dormant, so they will produce fewer electrical stimulation, electrical impulses. That's an interesting way of doing things, but it's also dangerous. And there is not much you can do about it. I mean, the brain shuts down the blood. And it shuts it down completely when the type of acoustic stimulation goes beyond a certain threshold. So if you're operating a jackhammer and you're breaking the asphalt in front of your house, well, you better wear some protection, because that's going to shut down all of your blood urination system. Well, you don't do that often, but people that work with that every day will find that their brain has shut down for a long time the blood urination on the basilar membrane. Now, how long it takes to repristinate, to restart the blood circulation, well, I can give you an order of magnitude. If you shut down the blood for, let's say, an hour, because you've been exposed constantly to an hour of sound, it takes you about 3 to 4 hours to go back to normality. So your hearing system will be diminished for a while. Problem is, if you keep doing it, as soon as you restart the noise, it will shut it back down. And eventually, what's going to happen, it's like plants. If you don't water your plants, they will die. And it will happen the same way to your hair cells. And it's pretty interesting to see what happens. You will start seeing your hair cells floating in the perilymph. So it will detach literally from the basilar membrane, and believe me, there is no surgery that can place them back in the place where they were. It's like losing your hair. So let me give you some numbers so you have an idea. In Italy, about 7% of the younger people have hearing problems. It's a horrible number. Think about it, 7%. You know what caused it? Well, simply keeping the music too loud. I mean, especially when you have, in-ear earbuds or headphones. It's a problem because when you go outside, there is traffic noise. You pump up the volume in order to hear the voice speaking, or even more, to hear the music undisturbed. And that is a primary cause of hear loss. Much more than we can think. And to give you an idea of what this turns very quickly into, just think about what happens in the US. In the US, younger people have hearing loss to a much wider percentage. I'm talking about 14 to 15%. That's really dramatic, because these people will reach my age and will not be able to enjoy music anymore. And believe me, it's not a good thing. But in some cases, not even have a conversation. And remember, if you think you can solve problems by simply putting on a hearing aid, believe me, you don't solve the problem, because you are trying to reconstruct information that is not there. Let me show you an image. This is a microscope, electron microscope image of the cochlea. So looks like I lied for about an hour now, because you don't see any of those hair cells that look like little rulers planted in a bed of rock. No, it doesn't look like that, as you can see. Actually, as a matter of fact, the cochlea contains a double layer of oscillators, basically. And that is also to obtain, to stratify also the dynamic range of the system. So you need to have a certain geometry in order to maximize the dynamic range of the receptors. But I won't get into the details of this. I just wanted to show you what it looks like in real life. Okay, I have a slide that I forgot to remove, and it's once again one of those slides that doesn't serve any purpose whatsoever, so just ignore it. And I wanted to come to discussing some of the consequences of the structure of the hearing system. So the first thing that I wanted to tell you that derives from the fact that you have receptors that are not infinitely selective, but they have their own bandwidth, is the so-called first-order effects of superimposed frequencies. Okay, imagine having two sounds. Then we'll discuss what it means in terms of physiology of the hearing system. You now have two sounds that, two pure sounds, two sinusoidal sounds that are a very close frequency to each other. So F1 and F2. So we assume that the distance between F1 and F2 is very, very small. For example, around 5, 10, 15 hertz, no more than that. Now, if you try that, you will perceive a single sound at a frequency f equal to f1 plus f2 over 2, so it's the average between the two, which is modulated at a frequency which is f1 minus f2 over 2. Now, why is that? Well, there is a simple explanation, but it starts from an assumption. The assumption is the two frequencies are now hitting the same hair cell, and the hair cell, because of the two frequencies are very close to each other, and the selectivity of the oscillation, selectivity of the filter is not small enough, not high enough, the same hair cell will perceive both oscillation. So you will perceive the sum of the two sinusoids. If we had an infinitely selective system, the first frequency will be perceived by one hair cell, and the second frequency will be perceived by another hair cell. But this doesn't happen, because the two frequencies are so close that the same hair cell will perceive the sum of the two. So, just by saying this, you can see immediately the result, the consequence of this. You have, let's say, this is the first frequency, sine of omega 1t. The other frequency is sine of omega 2t. And because each hair cell that will oscillate will perceive the sum of the two, more or less, you can easily use any of the trigonometric rules in order to turn it into a product of two sinusoidal signals. For example, you can write it as 2 sine of the half sum multiplied by the cosine of the half difference. Correct? That is what I was mentioning before. The first term is the note that I hear, which is the average of the two frequencies. But there is a term that oscillates very slowly. We said before, let's say 100 hertz for the first frequency and 110 hertz for the second. So the oscillation will be at 105, which is the average of the two. But the modulation will be at 10 divided by 2 hertz, so at 5 hertz. So I will hear something that goes up and down in volume at half that speed, half the difference of the two frequencies. As a matter of fact, I will actually hear it not at half, but at 10 hertz, because I'm sensitive to the power of that signal. So it will go up and down at twice that frequency, which is 10 hertz. I have an example here, which I hope I'll be able to play because I didn't test it before the beginning of the class. So let me see if it works. There is a door open, so I don't know if it works, but let me try. Here's what I'm going to play. We have 100 and 110 hertz, so it's exactly what I mentioned a minute ago. This is the type of when you show the combination of the two cosinusoids, okay, you will see that the result of that combination, so it's this particular formula, showed up there. As you see, the sinusoid is at 5 hertz, but the magnitude, because of the reversal, will be at 10 hertz. Okay, does that make sense? All right, so let's play it. Let's see if it works. Hopefully it will do something. It's a little distorted, but it should give you an idea. We started from two sounds at 100 and 110 hertz, and then the 110 starts going down in frequency until it approaches 100 hertz. So you can hear that it starts from 105, and in fact it's slightly detuned, and then it goes down, it approaches 100 hertz, but it stops beating. You lose the first order beat, musical beats. Let me try again to see if it gives you a better impression. Okay, so that's it's interesting to notice that that thing that appears to be so dynamical is not dynamical at all. The signal is a constant signal. We just sent two constant sinusoids, and we perceived something that, you know, dances around a great deal. We perceive the signal as dancing around. Let me be careful about these words. That's how we perceive it. It's not the way it is. As a matter of fact, these sort of things are also even exploited by for musical effects. For example, Jean-Claude Risset is a very famous musician who actually devoted a great deal of his activity in trying to create a catalog of sounds and examples that made people that worked in this area go crazy. But it was also fun. He has this was the example number, and they're all numbered, so you can do, okay, let's work with the example number 276. Let's see what we can do. And you discover a lot of interesting things that he did. So in particular, he came up with some ideas on how to be creative about musical beats. This is an interesting example that I stole from Perry Cook from Princeton University. Perry Cook is a famous researcher in Princeton University. He's famous also for the virtual Foley effects. So you know Foley effects are? Mr. Foley is the first guy who did audio effects in the movie theater without having any sound. So he was using coconuts, like in to make the galloping horses sound. He was using, you know, salad leaves and many other things, and the stones, all kinds of stuff to create the background noise. And he had a toolbox that was kind of fun that you could use in order to do this digitally. It's not the only thing he did. He did a bunch of very interesting things. But anyway, he went and dug this example out, and this is kind of interesting because it has basically a combination of 7 sounds, each one of which has 7 harmonics inside. Okay, so the choice of 7 is not incidental, to be honest. 7 is a number that will explain some of the things later. First of all, it's a prime number. And when you do the combination, you will see that it creates all kinds of varieties of musical beats. Anyway, you're familiar with the idea that a complex sound, a complex stationary sound, will have multiple harmonics inside, right? This is part of the representation of periodic sounds using the Fourier series. So if you have a sound that has 7 harmonics, it will be richer than the sound of a simple sinusoid because it will also have multiples of the fundamental. Now, let's take the first one. The first sound is 100 hertz, so it will also include the first harmonic at 200, then the third at 300, 400, 500, 600, and 700. So you have 7 spectral lines superimposed to form the basic Lego block for building this combination. Then if you take a second one, if you take, for example, the same kind of sound with a slightly different fundamental, so the lowest of these frequencies, and you place it at 100.1 hertz, the harmonics will be at 100.2, 200.2, 300.3, 400.4, and so on. So if you look at if you look at them pairwise, you will see that musical beats between the first fundamentals will be 0.1 hertz, and the distance between the two. But the distance between the two first harmonics will be 0.2, and the distance between the third harmonics will be 0.3, and so on. Now imagine doing this with another one such sound at 100.3, 100.2, in which case you will have the harmonics at 200.4, 300.6, 400.8, and so on. So now we're playing around with 7 of such sounds with different fundamentals: 100, 100.1, 100.2, 100.3, 4, 5, and 6. So each one of the harmonics will beat at completely different frequencies because they will be proportional to the fundamental. So they will form all forms of musical beat patterns at the end. What do you expect to happen when you put them all together? Well, you will have a very varied variation of musical beats that will change the color of the sound constantly because the weight of each one of their harmonics will change over time at a different speed and a different rhythm compared to the others. And dulcis in fundo, as we say in Latin, or as people said in Latin, let's remember that the rhythm of this variation will be aptary. We have 7 of them, right? So you will not have a regular rhythm. You will have an aptary rhythm. So the Balkan people will be very happy because the tradition of aptary rhythms comes from there. Well, I just discovered, I was just thinking about, you know, Take 5, Dave Brubeck, right? That was a 5/4 rhythm. He also wrote Blue Rondeau à la Turque, 7/8. Why do you think he was using those rhythms? I just found out that he was doing the military service in all the areas of the Balkans, and so that's why you have that kind of stuff. And he's not the only one. You think about Avishai Cohen, who has a lot of interest in polyrhythms that have multiple unusual rhythms. He also bases, he's a multicultural cauldron that puts together many cultures, in particular rhythms from the Balkan areas as well. So that's kind of interesting to see. Anyway, let's play this so you can have an idea of what I'm talking about. You will first hear the basic Lego block, the 100 Hertz sound. Then you will have all the combination of all of them together. Then you will only listen to how the 7th harmonic, if you remove everything but the 7th harmonic of all of them, you will notice they will have exactly the aptary rhythm. It will be more audible how you have the aptary rhythm at the end. So let me try this. Basic sound. Now all together. Count, it will be 7, okay? Aptary, right? 1, 2, 3, 4, 5, 6, 7. So if you want to have unusual rhythms in the changing of the color of the sound, work with multiples of the root. So if you want an aptary rhythm, work with distances that amount to 7. Okay? That's an idea. So it's kind of interesting to see what you can do with this sort of things. I mentioned before, there are people that actually do it on purpose. Of course, there is a lot of stuff you can do in electroacoustic music. But even in, you know, more popular music, you do that. You can exploit this sort of things. In jazz, I mentioned before Avishai Cohen. There is a piece that I can remember. He was playing, he played with the bass and singing, just bass and singing. It was It's Been So Long. Does anybody know that song? It's Been So Long. Well, you're a bass player, right? So you must have played that, right? It's a must. You want to learn to play. It's like a Stairway to Heaven for a guitarist. You go to the store, they kick you out because you play Stairway to Heaven. Same thing. For you, the Stairway to Heaven will be, it's been so long. So it's been so long, there is a moment in which he plays simultaneously two notes, so they will form musical beats. And surprisingly enough, the distance between the two notes is exactly the rhythm of the song. So that's done on purpose. The musical beats don't stop at proximity. They also work at proximity between harmonics, or proximity between multiples of the notes. For example, if you take two sounds as F1 and F2, and F2 is slightly off to F1, for example, 100 Hertz and 205 Hertz, to give an idea. So it's slightly off twice the frequency of the first one. You no longer have the problem of that the same hair cell will perceive the music, the same two frequencies simultaneously. You will have two separate regions of the basilar membrane that will be excited by the two tones independently. So there is no longer mixing in air. This is clear, right? The reason why this doesn't happen is because the bandwidth of each one of the hair cells is more or less 1/3. Am I saying something that makes sense to many of you? Well, of course you should know, so I don't even ask you. Do you know what I mean with a minor third or a major third? That's pretty much the bandwidth of each one of your hair cells, just to have an idea. And it changes. As you move in frequency, it will change. So if you have high frequencies, a minor third or a major third, depending on your sensitivity, will be quite wide in terms of frequencies, but the low frequency will be quite compact. Okay? So because we're talking about two frequencies that are approximately 1 octave apart, this is not going to happen. That means that the two frequencies will excite two separate clusters of hair cells. So you can have the same kind of musical beats that you had before. On the other hand, the brain is actually quite amazing. The brain will receive these stimulus in the form of electrical train pulses, pulse trains, sorry, two pulse trains. Despite the fact that they come in, let's say, in pulse modulated form, the brain will still be able to track the phase variations of the two signals and how the phase variations will interfere with each other, will form the wave shape. Let me give you an example. Well, first of all, we will have a tone beat at a frequency that is now F2 minus 2 F1. But instead of being a magnitude beat, it will be sort of a phase beat. So there will be something that changes. It's hard to detect how, but at a rhythm that is basically at twice at F2 minus 2 F1. Okay, so if it's 205 and 100, it will be a 5 Hertz. You have to be careful because, like I said, it's no longer amplitude modulation, like in the case of the first order, but there are cyclic changes in the wave shape. Let me show you what I mean just by showing you how the two things mix together. As you see, the magnitude is nearly constant, but the phase changes. You have a change in the wave shape. Can the brain, track such changes, even if it's working at the brain level now? Can you track them? Well, the answer is yes. Now, I doubt, honestly, that I will be able to render it well to you just using a pair of speakers in a reverberating room. I'll try anyway, but I'm not having high expectations on that. But definitely, if you put on a good pair of headphones, you will be able to hear this cyclic change. And at the end of the class, if you have earbuds and you want to try, just let me know. I play this for you with little hope. If you're close, you can hear it, but from there, probably not, right? I'll try again. If it doesn't work, we'll just move on. Can you hear it a little bit? I can, but I'm in the back and I'm very close to it. Anyway, so that's the idea. So it's sort of a demonstration of the fact that we do have a very sensitive machinery installed in our head. And so we can actually track such fine-grained details in the signal. People used to think that we're not sensitive to phase, especially at high frequency. We're not sensitive to phase. I heard it so many times, especially when I was your age. People believed that all that mattered was the magnitude spectrum. The answer is no, it's not true. It's absolutely wrong. We are very sensitive to phase. You can do a lot of things to change the shape of signal just by operating on the phase. You can even reconstruct the speech just from the phase of the signals. So there are lots of things you can do. So it was fundamentally wrong. If you look up the dictionary and read some of the descriptions that are of some words like timbre, the color of the sound, there is no definition that people can agree about in describing timbre. So be wary of what you read, especially when it comes to reading definitions on dictionaries. And I will say something that my wife will hate me for saying this, because she's a strong believer in, don't use Wikipedia. As a matter of fact, today things have changed, but the only place where I could find a reasonable definition of timbre was actually Wikipedia. All the other dictionary definitions were really wrong. So sometimes it can be useful also to read on Wikipedia some things. We'll come back to the definition of timbre. For the moment, I just wanted to focus on this idea. There is one thing that I wanted to mention, which is the notion of consonants. Consonants. Well, first of all, let me tell you a couple of things. I'll do this on the blackboard if I can find a piece of chalk. Yes, I have a very small piece of chalk, so I'll write half of what I want to say with the chalk and the rest with my fingernails. So be prepared. Okay, so here's the basilar membrane. The basilar membrane, we indicate the geographic position on the basilar membrane using, x expressed in millimeters, just to give an idea. If I produce, and let me use another axis here, okay? The other axis is f, frequency. In this diagram, I want to write what happens when I take one specific hair cell, for example, the one that is maximally tuned around 1,000 hertz, just to give an idea. And how does that cell respond to an impulse, for example? Well, what I want to find out is what the frequency response of the hair cell is. Therefore, this is 1,000 hertz, and I have the maximum response there, and then this could be the frequency response of the hair cell, okay? Now, how does this translate onto this diagram in order for your brain to interpret it, to interpret what's going on? If you know that each hair cell will have a frequency response that is kind of bell-shaped. Okay, think of it in these terms. Now, let me do the opposite. I'm here, I want to know what the firing density is. So the brain receives roughly just a bunch of impulses, electrical impulses, from each one of those cells. And because we have 30,000 of them, they will be very densely packed in this interval, correct? So if I now produce a tone at 1,000 hertz, so I'm generating on the basilar membrane a tone at 1 kilohertz, what will happen to the density of those, to the firing density? Well, it will take a similar shape though the meaning will be kind of different. So the hair cell that is placed here, it will be the location X such that the resonance at the maximum resonance will be at 1 kilohertz. So this is the position of that particular hair cell that resonates at a natural frequency of 1 kilohertz. On the other hand, there will be a bunch of others that will react to 1000 hertz, but a little less. So you will have this will be the maximum, then you will have a few more around it that will react to 1000 hertz. So that firing distribution actually looks very much like the frequency bandwidth of each one of those hair cells, except here everything is written in frequency like hertz, and here it's written in millimeters. But what I'm saying is the width from here to here corresponds to the location, the distance between all the hair cells that correspond to this bandwidth. So there is a one-to-one correspondence between the two. Remember, they're not the same diagram, so don't get confused. This is frequency response of one hair cell, and it will change as you change the hair cell. So if I consider another hair cell, will be slightly different. For example, at 998 hertz, the next one, right? To give an idea. So this tells you that our filter bank is not infinitely selective as far when it comes to sounds. The ideal system would have a bunch of Dirac impulses, right? Spikes, to give an idea. Now, how does this translate into understanding when there are multiple tones? What does the brain do? Well, when there is a single tone, the brain does something that is very simple. It looks for a peak, and it tracks the peak, right? Because the situation is similar to this. It's pretty easy to find out at what frequency the sound, the pure tone is, because you just have to look for the maximum of that shape. But when there are two tones, what happens? The same diagram with two tones will look like this. Superposition of two that are like this, right? So the result could be like this. If they're far enough, you might have something that goes like this. If they're farther again, you will have something that goes like this, even deeper than that. Can you see that? Now, how hard does your brain have to work in order to tell the two frequencies apart? It really depends on the depth of the valley between the two mountains, between the two peaks. If the two peaks are too close, you won't be able to distinguish them. But if the two peaks are far enough, you will have a valley in between, and your brain will be able to tell. It will say, okay, there are two sounds here, and I can clearly tell because the shape is the bimodal shape of two tones that excite a system that has limited resolution. This idea of resolution, we'll come back to that later, because now we're going to have to talk about, frequency time processing, so short space Fourier transform, short time Fourier transform, so analysis of the spectrum as it evolves over time, all this sort of thing. So resolution will be your friend for at least another 10 days. So be happy with the idea. You are going to have to walk hand in hand with that for a while. But once you grasp it, it's going to be so much easier later on. But look at this. This is not possible to discern. This is harder to discern. This is easier to discern. The level of hardness or of difficulty is also kind of indicative of your level of discomfort when you perceive sounds that are together. It's not the only reason. It's one of there is a strong correlation between your level of discomfort when you have tones that are next to each other, related to how hard it is for your brain to tell the tones apart. In a very crude fashion, let me tell you that the consonant somehow is very sensitive to this idea. When you have two tones, two simultaneous tones, and you want to tell them apart, well, the discomfort that you have in trying to do so will be called dissonance. Okay, we call it dissonance, and the complementary concept it will be consonance, of course. So if you have two tones at the same frequency, of course, that's the very definition of consonance. So they're the same tone, so there's not much you can tell. If you separate them about a fourth, okay, you have maximum dissonance. Pay attention to the two tones. Ow. Now, today it's no longer true, but you know, when you bang on the piano and you bang on two tones that are right next to each other, usually you say, okay, I'm doing something dissonant here. You don't say it, so usually the mother will kick him back to the bedroom. But that kind of tone is usually quite dissonant. It's considered dissonant. If you go that, oh, by the way, I didn't say, about a fourth of what? A fourth is more or less half tone, a fourth of the critical bandwidth. What is the critical bandwidth? Well, it's exactly this frequency response of each one of your cilia. And I've already spoiled the surprise because I said before that it corresponds to a third minor, more or less, to a minor third. So if you're playing a C, the limit of the critical band would correspond perceptually to, let's say, E flat, to give an idea, more or less. So you have a perceptual idea of what it means. So about a fourth of critical band is a fourth of a E minor, which corresponds to a half tone. Right? So it's two tones divided by 4 is one half tone. And there it is. In fact, I just played it, and it corresponded to a half tone. Half critical band is a distance of one tone, more or less. More or less. It changes from bandwidth to bandwidth, but it's more or less one tone. And people consider it 40% consonant. What does it mean? That means that someone, and usually these are American universities in the 70s and 80s that did a lot of perceptual experiments that were extremely useful for designing algorithms for compression and encoding. Well, they asked people, they paid $10 for each person to go and undergo the test. And the test consisted in pressing a button saying how dissonant it was after being exposed to a bunch of test tones. That's simple enough. You might think that it's kind of a stupid way of doing things, but believe me, when you have a sample size in the order of several hundred people, you can already establish something useful. So let me play the half critical band. A little off, but it's about one tone. 3/4 of a critical band. It's a third minor, but not high enough. And one critical band is 100% consonance, which is, in this case, more or less one minor third. Okay, so you go from 100% consonants when they correspond to each other. Let me see if here. You go to maximum dissonance here, which is half a tone, all the way back to perfect consonance, which corresponds to the minor third. Because we're used to that. It's also related to our own background, musical background. We've all been exposed to tonal harmony, so we all know what a minor third is. We all hear it every day in the sad songs. And so we perceive it as a normal thing, as a consonant thing. What about pitch? Now, pitch this is consonant, so we were considering two tones at the same time. Now, here we want to consider a single tone. Single tone for us means understanding what pitch is. Pitch is the subjective impression of frequency. Which note am I banging on? Right? On the piano. So, subjective impression of frequency, well, it really is less simple than it might seem to understand what it is. Because we could say that if we have a complex sound that is made of a bunch of spectral lines, the fundamental frequency tells you what the pitch is. but it's not necessarily true. And actually, you are exposed to this kind of situation because you speak on the phone all the time. And usually on the phone, the fundamental is missing. Not because the person is missing the fundamental, but because the phone cuts it off. And not because the phone is not able to produce it, but because people don't like it. You might be surprised about this, but a few years ago, there was a study in which they kind of interviewed a bunch of people, asking whether they agreed about the possibility of reinstating the fundamental as part of the, it's important to have a nice speech, the nice quality speech. And they did some perceptual tests, and people didn't like it. People preferred to have their voice altered by the phone. This actually dates back over 1 century ago. The early phones were based on carbon granule microphones that could not produce anything below 250 or 300 hertz. So anyway, the fundamental disappeared. So your voice was very nasal, very high-pitched. No, not high-pitched. It was still the same pitch, same period, but didn't have any low frequencies in it. And in 1 century, we learned how to perform the reconstruction of the fundamental, believe it or not. I have an example that I'll play later where you can tell it's the same pitch, but it's just devoid of some of the frequencies. So we are able to detect the pitch even in the absence of a fundamental. So yeah, people voted not to have it, basically. And the only case in which you hear full bandwidth is when you do teleconferencing, when you do Skype or whatever it is that you use. Then you hear the fundamental. But to people, it's like the choice of not reinstating the fundamental was like the choice of doing teleconferencing without the video. You're at home with your slippers, maybe you're a woman and you're wearing big curls, and you're brushing teeth, or you are in the bathroom while you're answering the phone. People don't want to know. You're doing it, it's your problem. You just don't want you want to have your privacy while you do that. And so in a way, you are not giving up the level of privacy that is afforded by not having the fundamental restated. So people chose that. So that's a typical case where you don't have the fundamental. Actually, not having the fundamental trained you to learn how to reconstruct it. And now we're all able to do that. And so we can use fundamental detection in order to do pitch tracking. You have to do something else. And we'll talk about that when we talk about pitch tracking, okay? It's a psychoacoustic variable, so it really depends on your psychoacoustic subjective sensitivity. For example, if you have perfect pitch, okay, if you orecchio assoluto in Italian, if you have perfect pitch, you might be more sensitive. It might be a disadvantage to you as a musician sometimes, but you are in a situation of advantage. In the sense that you will be able to identify more notes, you will be able to identify more changes. The pitch of a tone allows you to identify the note on a musical scale, but also that depends also on the culture. For example, Middle Easterns are far better than we are in detecting pitch because they use scales with many more tones, with multiple intermediate tones. So they're trained to that, and we're not. We're used to detecting the same tone that there are on the keyboard, on the piano keyboard, 88 tones. Maybe slightly more because now you can extend that virtually in other ways. So let's say that you're sensitive to more or less 120. You're trained to listen to 120 tones. Your ability will tell you in a minute what it means in terms of hertz. So I have some examples here that also tell you how complexity of the tone can be deceiving or can be decisive in assessing your own sensitivity to pitch. However, before I play these examples, I wanted to mention the fact that one reasonably widespread approach in measuring your sensitivity to pitch is the so-called assessment of the just noticeable difference, which is the smallest variation of frequency that we can perceive. The experiment is very simple. You sit down with headphones, and I play one tone followed by the same tone, and you'll say, okay, it's the same. If I play you one tone and a slightly different one, you don't detect any difference, you don't press the button. And I increase it or do it random. Every once in a while, you will perceive the difference and press the button, right? At the end, you collect all of your statistics with a bunch of people from different cultures, from different races, from different genders, from different, all kinds of things, and you do correlations, and you measurements and correlation. So at the end, you will discover that some very obvious things, that the lowest perceivable frequency is actually quite low. It's 20 to 30 hertz. The highest perceivable frequency is obviously between 15 and 20. We all know that. We also know that the ear is maximally sensitive to the frequency, to the pitch, in a very specific range, which is 1 to 0.0 kilohertz. Didn't I tell you that? I told you before that we are machines that are maximally tuned for interpersonal communication. That's pretty cool. And in fact, 1 to 4 kilohertz, 1 to 4 kilohertz is exactly the range of the speech. But the J&D is actually what is normally used in order to assess the smallest variation of frequency that we can perceive. And I'll give you a number in a minute, but I'm only after putting my hands forward and telling you about some disclaimers. This is only true in very simplified conditions, because our perception of pitch is extremely varied depending on the content. And in fact, let me play this example. This is a pure tone. Hopefully it will not distort. My hope was not well placed. This is a complex tone, but not that complex, just a triangular wave shape, so it has a bunch of harmonics above it. I don't know why this distorts so much, considering the brand. Then we have, this example is pretty cool. Actually, I like this example, so I'm going to play it twice for your own enjoyment. This is an example that has a 1 kilohertz burst that lasts about 40 milliseconds initially. It's a train of bursts, and it will shorten and shorten progressively as time goes by until it reaches the duration of 2 milliseconds. And then I will ask you a question, so be prepared. I won't grade you on that. Okay, what did you notice? You noticed at the beginning you could tell what pitch there was, and you noticed at the end that you couldn't tell anymore what pitch it was. And it wasn't the fault of the speakers, believe me, at least that. That wasn't the speaker's fault. It's actually due to the fact that your ear has an integration time. Okay. Do you know what I mean when I say an integration time? Remember what the impulse response is. Okay, look at this shape. This is the frequency response. What does it look like if you look at it? Doesn't it remind you of a Gaussian? So because you're fresh of memory when it comes to math, what is the inverse Fourier transform of a Gaussian? You know, if you want to find out what the impulse response is. I knew you didn't remember, so you better go back and find out. The Gaussian function is an auto function of the Fourier transform. Therefore, if you take a Gaussian and take the Fourier transform, you get a Gaussian. The only thing is that the signal will have a spread, and the Fourier transform will have the inverse of the same spread. So if I make it spreader, if I spread it out and I make it wider, it will get narrower in frequency, just to give an idea. Okay, so remember that Gaussians are quite important. So if you look at the frequency response, you have a bell-shaped function. If you look at the impulse response, it will still be a bell function, more or less. So it will have a duration. That duration is sort of an integration time. Now, the duration in this case is in the order between 50, 60 milliseconds. If anything doesn't last long enough, It will be very small compared to the 60 milliseconds, and you will count it. The ear will not have enough time to be able to detect frequency content, will not have time to be able to discern frequency content. Actually, for that kind of duration of 2 milliseconds, all the possible cilia will be excited because it will receive like impulses. It will look like an impulse. When you have an impulse, it contains all possible frequencies inside, and so it will excite all possible hair cells of your basilar membrane. That's why you perceive it as a white noise or an impulse noise. Did you notice that? Now that I told you all these nice things, let me go back and play it again so you will notice many more things that you noticed before, hopefully. Okay, let me go back. It's this one. Okay, now it should be pretty clear. If events are not long enough, we won't detect them properly. So we have a loss, because of our hearing system, we have a loss of frequency resolution, but also a loss of temporal resolution. So our ability to detect events over time is altered. Obviously, we are particularly sensitive to pitch when it comes to modulated signals. There is an interesting example, which is the cello. Does anybody play cello here? Okay, well, enjoy the sound, because this is one of those cases where the pitch is technically hard to detect, but we perceive it so naturally because we are used to that kind of tone. So. A sound that is so complex, and yet for us it's very natural to detect the pitch. Complex because there are modulations of all sorts. You are creating vibrato with the motion of your hand. You're also creating harmonics that are excited. You are creating interference with the harmonic sympathy vibration of the other strings. And you're creating overtones. So it's an extremely complex sound. There is the intervention of the whole body of the instrument that changes and alters the frequency content of the sound. It's also not a harmonic sound. It's slightly enharmonic. So the frequencies, the partials that are supposed to be at multiples of the fundamental are not, because of the rigidity of the system that alters the pitch of the harmonics. And there are situations where the situation gets even worse, like inharmonic tones of a gamelan tone. We are still at the point in which we detect the pitch, as we would with any of the mallets, for example. So if you take a vibraphone, if you take a xylophone or marimba, whatever you want, you will be able to detect the pitch, despite the fact that the partials are definitely far from the multiples of the fundamental. So understanding how our perception of pitch works for this sort of tones is extremely difficult. Yet, we can still do a lot in a very rough and engineering sort of way. Oh, by the way, I mentioned before that I would show you the comparison between the missing fundamental and with the fundamental. I have two examples here. This is the sound with fundamental, and this is the sound without. Okay? It's the same pitch, but it's just weaker in many ways. But we're missing the fundamental in the spectrum, and yet we perceive it anyway. So it's not related to the presence or the absence of the fundamental. So I just wanted to prove the point by doing that. I said before that despite the complexity of the notion of pitch, we can still say something about our sensitivity in a very rough and some cursory sort of way. So I mentioned before the term JND, which stands for just noticeable difference. And I also told you how to measure it. You can do it. like I said, we all have different JNDs, especially if you're a musician, if you're not a musician, if you're trained, if your ear is used to listening to music, if you come from the Middle East, or if you come from Italy, if you come from the US, or if you're a male or a female. Oh, yes, if you're a male or a female, there are differences. Women are particularly sensitive to changes in frequency at higher frequencies than we are. Because, well, it's nature again, nurturing children. Even if today we are both doing the same thing, male and female, in the past centuries it wasn't that way, and so our hearing system has become accustomed to differences and has adapted to the situation. Yet, if you do statistics, an average statistics on anything, and you want to get some measurement that makes sense and is safe for all possible situations, there is a very, very simple rule. For medium intensity sinusoids, and I insist on the word sinusoids, the just noticeable difference is about 5 per thousand of the fundamental frequency of the tone. Well, in this case, of the frequency of the sinusoid, because we don't have other tones other than the fundamental. So, which means that if you have a tone of 1,000 hertz, we can detect changes in the order of 5 hertz. If you have it at 2,000, it'll be 10 hertz. If you have it at 600 hertz, it will be 3 hertz, plus or minus 3 hertz. But if you go below 6 hertz, 600 hertz, it will flatten there. So if you take 500, it will still be 3 hertz. 400, 3 hertz. So all the way to 600 hertz is proportional, 0.5%. Below 600 hertz, it flattens at 3 hertz. So that's the magic number. You might think that this is not very useful right now, but you will find that you need it for designing systems that perform frequency analysis. You want to know, you want to design the length of the filter, you want to design the length of the window, you want to design the length of the FFT, not of the window, in relation to the window, in order to have an error of localization of peaks that is below audibility. In that case, you have to know the JND. So I'm telling you a bunch of things, but believe me, remember them, because otherwise you won't be able to design systems later on. Have you ever tuned a piano? Has anybody ever tuned a piano? I have. And I didn't succeed. I was very, very bad at doing that. So I had to call someone else to retune it after I did it the first time. So there is an inherent difficulty in doing this sort of things. So I have to warn you, don't try it yourself unless you know what I'm talking about. There is a strong dependency between pitch and intensity. That's one of the reasons why it's so hard to tune a piano. If you tune a guitar, it's not much of a big deal. If you tune a guitar, you have an instrument that doesn't have a super high dynamic range. So you can trust what you hear. But if you are an opera singer, it's really hard to stay in tune. If you are, because you have a very powerful voice. If you are a piano player, you need to have tuning done in a certain way. Because there is a very strong dependency of the tuning of the frequency of the pitch on the intensity, on the objective intensity of the sound. There's a very interesting diagram here that I like to show because it's very indicative of what's going on. This diagram tells you that, well, first of all, you have two objective measurements here. Sound pressure level, which is an objective measurement, and frequency change. So this is expressed in hertz. How much do we need to change the frequency in order to perceive the same tone? So these are curves that describe iso pitch curves. They describe how to alter the frequency of a tone in such a way to be able to perceive the same pitch. So normally, diagrams that describe perception are diagrams that have two objective measurements on the axis, on the abscissa and on the ordinate, but the curves are curves that describe something that doesn't change in perception. So I have another diagram that I'll show you in a few minutes. This is one of those. Okay, so you will notice, okay, these numbers represent what you hear. For example, the 150 says it tells you what the frequency is when you perceived it at a standard condition. If you now alter the sound pressure level, let's do this. We take a tone at 150 hertz in control condition. We start increasing the sound pressure level, and then you have to reduce the frequency of this amount, expressed in percent, in order to obtain the same tone, to maintain the perception of the same tone. So as you notice, if I am an opera singer and I hear my own voice singing, which I hear very loudly because of the diffraction of the borders of my mouth, by singing louder, I'm going to have to do some adjustment in order to hear my own voice in tune. I'm going to have to lower my voice, sing lower, sing flat. The problem is, if you're sitting down there and I'm singing here, the tone that you hear down there is much lower than the tone that I hear. So you will hear my voice being sharp. So I hear it right and you hear it sharp. If I'm a soprano singer, which I'm not, and I'm singing at a higher pitch, and now I'm starting, and I tune my own voice because I'm singing louder, so I'm singing slightly sharper in order to avoid the problem. You down there will hear me slightly flatter because you hear a different level of intensity from the one that I hear. So my adjustment will be wrong. Do you see the problem? So what I'm saying is, that's why when you go to an opera, if you are in an opera choir, and so you sing along with the singers, you will notice a bunch of things that doesn't make sense to you. So usually the opera director, the director of the opera will tell the bass singer to sing flatter, and than he should, and the soprano singer to sing sharper, right? In order to compensate for that lack of judgment. And the opera singers will have to adjust. They will have to learn to sing out of tune in order for other people to perceive the correct pitch, believe it or not. This is just one example. Another example is the piano. You have a piano that is tuned in an environment that is highly reverberant and very small. It will be much louder than in an auditorium. Well, you're going to have to tune the piano using frequencies that are recorded for that particular piano in those conditions. Of course, now you can always say a real piano tuner will not use an instrument. Yes, if you're willing to pay for 8 hours of work, that's okay. But if you're willing to pay 80 euros for tuning your piano, well, you're going to have to be content with a piano tuner using the machine, right? In which case, you will use a machine that has already recorded the particular model of piano that you have at that moment, which could be, I don't know, a Yamaha C3, just to give you an example. So it picks up the Yamaha C3 and the environment that it's in which case you will have a certain recording of frequencies after having done the perfect pitch tuning of the instrument. Otherwise, the same piano brought to a different place doesn't happen because you have to retune it anyway. But if you took the same piano into a different place, it will sound out of tune, not just because of temperature variation, but because it was tuned in a different environment. So actually, this is also something that is a problem for the orchestration. If you do orchestration, you also have to keep, and you're doing really refined stuff. I'm not talking about simple big band or other simple things where you can perform a certain degree of self-adjustment. But if you take the orchestrators of the early 20th century, there is a lot of thinking that you need to do, because you have to group large numbers of musicians doing the same thing. And you have to be careful. If you have big ranges of intensity, you have to make sure that the perception will not sound out of tune. I mentioned last time, I mentioned the Bolero Ravel, which goes from a quadruple piano to a quadruple forte. And that kind of variation is really dramatic in terms of pitch adjustment. And most musicians do that automatically. Either if you play reeds, if you play double reed, you can do a certain degree of mouth adjustment. Also, if you play, you know, trumpets or anything like that. But if you play beyond a certain level, you have to do some retuning on the fly. And musicians can do that, but you can't really test it. So you just go by memory. You take you shift the curve of your trumpet in order to make sure that it will not completely be out of tune. Sometimes you can even do that. And in the Bolero, at the end, there are some places where you have intentional dissonances, especially in the climax. If you know the piece I'm talking about, there are some trumpet dissonances that are placed on purpose in order to create to force the listener to adjust to a new pitch. So it's an intentional operation that sometimes you do in order to favor the auto adjustment of your pitch perception. If you read the original manuscript, you will find there are notes that tell you that. So it's really interesting. You can learn a lot about psychoacoustics by looking at the original manuscripts, if you can find a copy of the orchestrators. It's an orchestrator is the quintessential engineer. If you, I'm having fun now because I'm taking lessons on orchestration, and it's really interesting because the orchestrator thinks in these terms, thinks in terms of perception, thinks in terms of adjustment, balance, and it builds the entire foundation of the musical piece in a very architectural fashion. You have melodic design, and then you have to build harmonic, orchestration, and rhythmic foundations in order to hold up that design. And it's really, really cool to see happen. Going on, and I'm going to take another few more minutes, so I apologize if I kind of go slightly overboard with this. I absolutely want to talk about acoustic intensity. Acoustic intensity is something you measure in objective fashion, but the perception of the acoustic intensity, which is defined as loudness, doesn't work that way. These are very famous diagrams that have been used constantly in the past decades. They're the so-called Fletcher and Munson isophonic curves. As before, you have two measurements that are objective, right? So in the horizontal axis, you have frequency. In the vertical axis, or in the ordinates, you have dBs. So you have loudness, not the loudness, sorry, the sound pressure level in dBs. So both measurements are objective measurements. And of course, the curves describe something that is constant in perception, exactly as we did before. But this time we're talking about loudness. So these are loudness, isophonic curves. So how much sound pressure level do I need to change in order for my perception of the intensity to remain constant? So if so first of all, what's a phone? These are isophonic curves. So that means that the measurement of loudness or perceived intensity is expressed in phones, which is the amount, if you take a sinusoid at 1000 hertz standard value, the measurement in dBs will be where you start from, and that's expressed in phones at that frequency. So you start from here. We are here, for example, at 1000 hertz. Here you have 10, so the crossing with the 10 happened exactly at 1000 hertz. So this is 10 phones. And then you move away from there by changing frequency, and by measuring the adjustment in the sound pressure level that you need to do in order to obtain a constant loudness tone. You do this for all possible intensity, and you obtain this kind of diagram. That means that the lower the curve, the higher the sensitivity. And incidentally, you will notice that frequencies that go from, say, 100 hertz all the way to 6,000, 7,000 hertz is exactly where you have the maximum sensitivity, which, by the way, corresponds exactly to the speech. So once again, our system, both for listening but also for producing utterances, will be designed in order to obtain maximum throughput in interpersonal communication. So another thing that you might want to consider as interesting is if I record something in a specific condition. So I'm in the studio and I'm recording jazz quintet with a saxophone player. You have a certain intensity of sound. And so let's say you're working on one of those average curves. Let's say you're working at an average pressure of 80 dBs at 1 kilohertz. So you're working at 80 phones of intensity. But then you listen to what you recorded in the car, and you want to hear the traffic sound outside. So now the level that you listen to is about 50. Now, because you're listening to the same content at a different condition, that means that it's as if the sound were going through a filter. Because, let me see. So you have to take the curve at 80 phones, and then you take the curve at 50 phones, and now you're listening to this, what you recorded this way. So you have to take it. You have to take the difference between the two curves, right? And that means that it's as if your piece went through a filter like this, which is the difference between the two curves. And incidentally, it's as if you were band passing the signal. It's band passing, so you are lacking low frequencies. This is why, because of that operation, you need to compensate. You need to compensate through some filtering. And there is a button, if you remember, it's called loudness, which is in the stereo system in your car and so on. Long ago, it was just a button that would, pump up the basses, and that's it, and a little bit of the high frequencies, and that's it. But that's not what loudness is. Loudness is something a little more sophisticated. Now in the modern cars, there is a measurement on the noise in the car, and so you can do loudness adjustment. So it really works like a physiological compensation filter that changes its frequency response depending on the level of noise in the car. This is why it's called loudness, because it comes from those curves. These are the intensity thresholds in their extremes. The top one is called the threshold of pain, and the bottom one is called the threshold, the hearing threshold. And they actually migrate over time, so they change, you get less sensitive as you grow older. You get less sensitive if you listen to your headphones too loud, and so on. So let me play a couple of examples, and I beg you to be a little more patient with me, because I have one last thing to tell you, and I'll be very quick with that. So this is an example that is not going to work perfectly because I don't know at what level it was recorded. But equal loudness example means that you are playing directly with the compensation. And it's, so we're playing a bunch of tones like that. This is already compensated. This is a bit too much. There are two examples because you don't know at what level it was recorded. Okay, it was just approximate, but I can guarantee you that these tones, if they were played at equal magnitude, you wouldn't hear the low one or the high ones. You would only hear the ones in vocal frequencies. All the others would disappear. So there is a strong compensation in order for you to be able to hear the low tones and the high tones. Okay? Last thing I wanted to tell you is this, because this is important. It's a so-called frequency masking. Remember I mentioned before that if you are listening to two simultaneous tones, you have a hard time telling them apart when they're very close to each other. Remember why? There is still the image here. When the two tones are very close to each other, you have a hard time having this discrimination of the results. This is the fire in density as it changes with the location of the basilar membrane. Now, in particular, if one of the two tones is very low in magnitude, it will have a very hard time surfaces from the mounting created by the first tone. So in a way, the presence of a strong tone will make it harder for a weaker tone to emerge. And this is called a masking effect. And it's due to the fact that you have a critical bandwidth, that your receptors have a large bandwidth, not a very highly frequency selective one. Now, this also ends up affecting your threshold of audibility. So if I already have a tone present at 1 kilohertz, let's say, this is now a linear scale. That's why it doesn't look symmetrical. It's not a Gaussian the way you would expect it to be. But so in a linear scale, if I place a tone at 1 kilohertz, fairly loud, so let's say 60 dBs above audibility threshold. So it's expressed in SPL. Now the SPL is 60 dB. Well, and I want to play a second tone. In order for the second tone to emerge from that situation, I will need it to be louder than it should be in order to be heard alone, because the presence of the first tone will mask the second one. So it's as if the masking tone lifted up the threshold of audibility, the hearing threshold, for the second tone. Okay? So that's called masking effect. I think I have an example I can play about this, but I don't know where I have it afterwards. Oh, before I play the example, let me tell you that this masking works also over time. So if I have a tone that is masking, and I turn it off, and immediately after I turn on the second one, it's as if the tone was still there. So it takes a little bit of time for your brain to adjust to the absence of the tone. There is some sort of a hysteresis behavior on the part of the brain. And this might surprise you, it's even anticipatory. So if I turn on a weak tone, and immediately after I turn on the masking tone, I remove even the weaker tone that started first. So it's anticipatory in effect. But it's, the anticipatory effect is much shorter than the effect afterwards. So if you want to picture the situation in a higher dimensional space, you can think of it like that. Your tone, the masking tone, is like a blade in the frequency time domain. So it's a sort of a blade lifting up, which lifts up a rug, a carpet. Okay? So you will have the masking tone that operates in frequency, but also over time, with even a slight effect on in anticipatory terms. To close, I'd like to play this last example that shows what happens with masking, and then we'll close the lecture today. You will hear a higher frequency tone that masks lower frequency tone, and then a lower frequency tone that masks the higher frequency tone. The frequencies are mapped on the slide. Let me play it for you. Did you hear? The second case was slightly more difficult because of the noise in the room. I'll play it one last time, maybe slightly lower in volume. Disappeared. Disappeared again. So, you know why it's important to know that this happens? Because right now we're working with the Fraunhofer Institute in Germany. We have a contract with them, so we have a close relationship with them. They designed MP3. MP3 is, in fact, an application of perceptual coding. And it's an application that heavily relies on this effect. So it's not just words floating in midair. This is actually what makes it possible to design perceptual encoding systems that allow you to pack more content in the same space. And I'm talking about an order of magnitude of compression. I'm not arguing, and I'm not talking about the quality of the result. I'm just telling you that if you tried in any other way other than perceptual encoding, something that exploits the weaknesses in your perception, you would get worse results. I can guarantee you that. So all the theory of encoding, decoding, perceptual encoding and decoding, which are the most effective solutions today for packing more information in the same amount of space, are actually based on exploiting such principles. Nonetheless, all the information I gave you today, which is very compact in form, will be very useful for designing system. So I'll keep, taking them out again and putting it on the table for you to remember. J&D, masking effects, perception of pitch, and so on. All these things will be extremely important for designing your system.